Tell me the Calc story.
A duck walked up to a calculus stand, and he said to the man, "Run in the stand."
Hey,
Bum bum bum.
got any derivs?
The man said,
No, we just sell integrals, but it's fun and it's fresh and it's all Kanano made. Can I give you a class?
the duck said,
I'll pass.
but the man said,
No, you can't pass calculus without learning integration, so too bad! Hi Duck, so today for your first lesson on integrals, I'm going to give you an introduction to, you guessed it, integrals. But before we begin to talk about integrals, one important question you need to answer is, how would you find the area of a curve? Everyone knows how to find the area of simple shapes like rectangles and circles, and this is the line of thought mathematicians followed hundreds of years ago. They realized that if they took a curve and created rectangles with the width being called the dx, they could find the area under the curve, and called this technique the Riemann sum. But one thing you might notice though is that this isn't perfect, because there are still some parts of the rectangle above the curve. So one way we can make this approximation more accurate is to just add more rectangles by making the dx smaller. But what if we never stopped adding more rectangles and had an infinite number of them, with dx being an infinitely small number? The sum of those rectangles would then be the actual area under the curve, and would be what we call an integral. An integral is a way to define areas in the function, and in this example you can see that the area between the x values 1 and 2 can be represented in this notation. But a problem with this notation is that we can't really do anything with it. Even if you knew what f of x exactly was, you can't just calculate the integral, you need it to be in a form that is easier to solve. This is where antiderivatives come in, which can be thought of as the opposite of derivatives. Whereas the derivative of x squared would be 2x, the antiderivative of x squared would be x cubed over 3. Because the derivative, and that's because the derivative of x cubed over 3 is x squared. That c you see at the end there is called the constant of integration, and it is very important. Because the derivative of any constant is 0, the integral of x squared could be x cubed divided by 3 plus any constant value. We just have no idea. However, when we want to find the area of a definite integral, meaning the area between two defined values of x, we don't need the constant of integration and instead solve for the antiderivative and subtract the value of the antiderivative at the lower bound from the value at the upper bound. And this is called the first fundamental theorem of calculus, something that will come very handy in your integration adventures.
Then the duck said, "Sheesh!" Then he waddled away
Waddle waddle.
till the very next day.
Bum 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 ba-dum.
When the duck walked up to the calculus stand, and he said to the man, "Run in the stand."
Hey,
Bum bum bum.
got any derivs?
The man said,
No, like I said yesterday, we just sell integrals, okay? Why not give it a try?
the duck said,
Goodbye.
but the man said,
No, Duck, it isn't goodbye. Look at all the ways integrals can help your life. Have you ever wanted to figure out the average rate at which a pipe pumps water throughout the day?
Alright, hello Mr. Duck. Welcome to day 2 of your integration crash course. Today we're going to be learning about how to find average value using integrals. Now, essentially what you need to know is this main theorem, is that if f is integral on the closed interval a to b, its average mean value on the closed interval a to b is the average of f equals 1 over b minus a, integral of a to b, f of x dx, right? So there are two major approaches to doing this, and your first one is going to be integrating using simple definite integrals, and your second one is going to be the graphical approach. Now, let's get on to our first example using the simple definite integrals. Now you have f of x equals 3x squared plus 2x plus 1, right? First, we're going to write out our average of f equals, and then we have our interval, right? So 1 over 2 minus 0, b minus a, right? Integral from a to b, so 0 to 2, and then just our function. So it's 3x squared, 2x plus 1 dx, right? Now, I made this an intentionally simple one to solve, but it's going to come out to be 1/2, and then you're going to just integrate using your reverse power rule, so it's going to be x cubed plus x squared plus x from 0 to 2, right? And then you're just going to solve your integral, so you're going to come here, and you're going to have 1/2, 2 cubed plus 2 squared plus 2, And since you have 0 and you have x's, it's just all going to cancel out. So this is going to become 8 plus 4 plus 2. So 14, divide that by 2 is going to be 7. Your average value is going to be 7. Alright, not too bad. Let's get on to example B. Now this one is a little bit more difficult. So you're going to be given a graph, and you're given an interval, and you're given a function. So 1 minus square root of 1 minus x squared. So that's not all too simple to integrate on its own. So what we're going to do is we're going to look at this graph, right? So as you can see, I've shaded in the area where you have, where you can just regard what the area in the curve is, right? So first, anytime you have a graph, what you're going to need to do is you're going to need to label what you know. So here, you know, this is going to be a height of 1, and you know this is going to be a base length of 2, right? And if you notice two shapes here, let me just move that 2. Okay, and now you notice two shapes here. There's a semicircle and a rectangle, right? So to find the area under the curve, you're going to do the area of the semicircle minus the area of the rectangle minus the area of the semicircle, right? So it's going to be area equals rect minus semi, right? And the semicircle has a radius of 1, so the equation for the area of the semicircle is pi r squared over 2. Since r is 1, it's going to be pi over 2. That's just a simple rectangle, so it's just going to be 2 minus pi over 2. Now, when you do the average value, you're going to get that you have 1 over 1 minus negative 1, which is going to be 1/2, integral from 1 to negative 1 of f of x dx. You can write it out, doesn't really matter. It's just, what it means essentially is it's just the area under the curve. It's going to be 1/2 the area under the curve. Since we already have the area right here, we can just do 1/2 and apply it to that. So the average of f, equal sign there, average of f equals 1/2 2 minus pi over 2, which is going to equal 1 minus pi over 4. There you go. That is your average value of f.
Then the duck said,
That wasn't bussin' though.
then he waddled away.
Waddle waddle.
Then he waddled away.
Waddle waddle waddle.
Then he waddled away.
Waddle waddle.
Till the very next day.
Bum 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 ba-dum.
When the duck walked up to the calculus stand, and he said to the man running the stand,
Hey, got any derivs?
the man said,
That's it! Stop acting sus! Duck, I'll glue you to a tree and leave you there all day stuck, so don't get too close.
the duck said,
Adios.
but the man said,
How about adios? You saying adios, huh? You ever thought about that? Look, try it out, okay? You can use separation of variables to solve even more challenging problems.
Alright, duck, we're going to be doing some separation of variables, using a little bit of integration and antiderivatives. So here we have the equation dy over dx equals 10x y squared. So usually there's going to be some parameters set. So here, f of 0 is equal to 1. This is important for a later step. So as the name implies, you want to first separate the variables. So here we have x and here we have y, and so we want to separate those. So since this is a fraction, we can do a little bit of dividing, a little bit of algebra. So this writes out to dy over x squared is equal to 10x dx. Now what we want to do is use antiderivatives, and we want to set these on both sides and do the antiderivative. So on the left side, we'll have negative 1 over y is equal to 5x squared plus c. Now this c is super important, because this is the constant that we need to use using the parameter that we set before earlier above. F of 0 is equal to 1. So let's use that. Negative 1 over 1 is equal to 0 squared plus c. Now this is equal to negative 1 is equal to c. Now we can solve this equation back. So let's rewrite this. Negative 1 over y is equal to 5x squared minus 1. Using some simple algebra, we finally get the equation y is equal to negative 1 over 5x squared minus 1. And we can rewrite this to equal f of x. Moving on, let's do some harder examples of it. Here we have a more difficult equation, but it is essentially the same steps. So let's follow them. Find y is equal to f of x, the particular solution to the differentiable equation with initial condition f of 0 equals 3 if dy over dx is equal to 3x squared y plus 2xy. Now, the wording differentiable equation and all these different parameters given to you should be an indicator to use separation by variables. So let's start. Let's rewrite our equation as 3x squared y plus 2xy, which is equal to factoring out y times 3x squared plus 2x. So let's follow the same steps as before. This is still a fraction, so we can write this out as dy over y is equal to 3x squared plus 2x dx. Now let's find the antiderivative of both sides. On the left, we'll have natural log of y is equal to x cubed plus x squared plus c. Remember the c. Always remember the c. If you don't have a c in these problems, you're doing something wrong. Now let's use the parameter f of 0 is equal to 3. Now we will get ln 3 is equal to 0 plus c. So c will equal natural log of 3. If we rewrite this, we will have natural log of y is equal to x cubed plus x squared plus natural log of 3. And putting e as the base for both of these sides, we'll be able to simplify down to y is equal to 3e x cubed plus x squared. And that is your final equation, Duck. Then the duck said,
You acting sus.
Then he waddled away.
Waddle, waddle.
Then he waddled away.
Waddle, waddle, waddle.
Then he waddled away till the very next day. When the duck walked up to the calculus stand, and he said to the man that was running the stand,
Hey, got any glue?
What?
Got any glue?
No, why would I? Oh.
And one more question for you. Got any derivs?
and the man just stopped. Then he started to smile. He started to laugh. He laughed for a while. He said,
Come on, Duck, let's walk to the store. I'll buy you some derivs so you won't have to ask anymore.
So they walked to the store, and the man bought some derivs. He gave one to the duck, and the duck said,
No thanks. But you know what sounds good?
I don't care what sounds good. Take this integration by parts. It also has derivatives.
Alright, little duck, welcome to day 4 of your integration calculus crash course. Today, we'll be going over integration by parts, which has what you've finally been asking for, derivatives. First, let's just quickly go over the theorem for integration by parts. It's actually really simple. The integral of u dv is equal to uv minus the integral of v du. This equation is fairly simple, and once you apply it to a question, you'll see that it's actually really easy to do. So let's start off with a simple expression right here. Find the integral of x times e to the x dx. So the first thing you want to do is pick your u and your dv values. So what you want to do is, for your u value, you want to pick something that you know how to take the derivative of, because that's what you're eventually going to your u value. In this case, we can take the derivative of either x or e to the x, so it doesn't really matter, and I'm just going to pick x here. And for your dv value, you want to pick something that you can take the integral of, and we know how to take the integral of e to the x as well, so we'll do that. Now, you're actually going to follow through, and you're going to take the derivative of your u, and the derivative of x is just 1, and you're going to take the integral of your dv value, and the integral of e to the x is just e to the x. So now that you have all these values, all you're going to do is you're going to go here and just plug these values into this equation up here. So I'm going to rewrite it just one more time. So we want uv, our u is x, our v is e to the x, minus the integral of our v, which is also e to the x, and our d value, or du value, sorry, which is just 1, and then of course dx at the end. So we actually know how to take the integral of this. This one you can just ignore, and we said up here that the integral of e to the x is just e to the x. So your final answer all in all is x e to the x minus e to the x, and of course you can't forget that plus c. Okay, now we're going to move on to example B, and this one's a little bit more tricky because it actually takes some thought to figure out what your u and your dv values are going to be. So, like we said before, you have your u, and then you have your dv, and your dv needs to be a value that you can take the integral of. Now, we can go of x squared, but we don't know how to take the integral of ln of x. So that means x squared is going to be our dv value, and we do know how to take the derivative of ln x, so that's going to be our u value. So we're going to take the derivative of ln x just for future use, and that's 1 over x, and the integral of x squared, which is going to be our v value, is x cubed over 3, or 1/3 x cubed, same thing. So now we're just again going to plug these numbers back into the formula. So uv, our u is ln of x times our v, which is x cubed over 3, minus the integral of v du. So our v value is x cubed over 3, and our du value is 1 over x dx. So what we see here is that we can cancel this x out with this x, make this squared, and we can actually just bring this 1/3 out front. So I'm just going to clean this up a little bit. Minus 1/3 integral of x squared dx. So we know how to take the integral of this because actually it's just the same as what we did up here, just like the last problem. So I'm going to rewrite this one last time, and then the integral of x squared is 1/3 x cubed. So this 1/3 with this 1/3 becomes 1/9. I'm just going to rewrite this for simplicity, and again, just like last time, you can't forget that plus c. So this is your final answer, and I hope you learned something, little ducky.
Then the duck said,
It would make my day. Do you think this store has any integrals?
then he waddled away,
Waddle, waddle.
then he waddled away,
Waddle, waddle, waddle.
then he waddled away.
Waddle, waddle, waddle.
Sheesh!